Okay, and now thank you for joining me for the Python section of the ninth data analysis bootcamp, hacking hypothesis testing. So it's a really important class to really just, I think, understand this effect of hypothesis testing and resampling. When I was working for a fintech startup, we only had like 60 clients or something like that, a very small amount. And really, the only way that I was able to build a model, it just was not enough data to really be confident in anything. But through hacker statistics, you're able to really notice subtle differences and it kind of emphasizes them. And I was able to find out what is really important in making that decision. Okay. Um, okay. So I think this is a really important class. And if it's a little bit confusing, I think it just requires you to practice with it a little bit and play around with this concept. It's why I introduced sampling in the first class, and we're kind of coming full circle, is to highlight, the things that we learned in that class, the effect of sampling. Okay. And then how hypothesis testing is that same works in that same concept. We're able to use that to get a more robust understanding of our data. Anyways, I'm gonna stop rambling. So here what we have, I'm doing a little bit of different stuff with Python or Seaborn today. So I create a palette, get bored of the normal standard colors right here. So just create another color or palette, and colormine.io is a great place just to go to get a different color palette. And here I'm going to do set palette. So this is actually what's setting the palette right here. I don't need to do these two lines. I just like to actually see what my palette is. So sns.color_palette. It's going to give you the ability to look at and see kind of how your palette is set up, and if you like to kind of move things around or change things around. Okay. I'm going to use this set style as well. So we're able to do a lot of changing on Seaborn using the set style. And this is a list of kind of everything that there's available. Here's a link to other things that I wasn't able to include. And so axis.face color, we're going to do this face color. Figure.face color, we're going to do this face color. Text color, we're going to do this. Tick color, we're going to do this. Tick color, edge color, and so on. Everything where we have the ability to change. So it makes them for some pretty cool plotting. Okay. So here what we're going to do is define our own little hist plot function that allows us to do kind of more for an effect in any sense. Okay, so in the plot underscore hist function that we're creating, so the first thing we're going to do is do subplots. In the next step, we're going to do is ax equals sns.histplot, data equals array, and alpha equals 0.8. Okay. What I'm going to do next is I assign this to an object. So I'm going to go for rectangle in ax.patches. It gives me a list of all of the items in my plot, and we're going to iterate through that. I'm going to iterate through and make the line width of the rectangles a little bit thicker on the outside and change the edge color to a different color. Okay. I'm going to add a title to my plot, label none, and plot type layout. Okay. So this allows you to kind of repeat this, so I don't have to do the same. It's not a lot of code, but you could do that in every cell, but a little bit nicer and neater to just plot it right here. Okay. And so my uniform distribution. So what I did is I randomly sampled from numpy.random.uniform, and this is where I use numpy a whole bunch, is this random function. It's amazing how much you need random numbers. So numpy.random.uniform, 1 to 100 sample size is the sample size that we set up here, so 500. Okay, and then I'm just putting this into a series, and you can see it looking right here. Okay, and if we do plot, not plt, plot underscore hist samples uni, the samples that we just created right there, get a uniform-ish distribution, and a little bit of random deviation will change that, but basically a random distribution of from the uniform distribution. Okay. So what I'm going to do here is I'm going to get samples means. Okay. So this is now plotting all of the sample means from this distribution. So I'm going to go ahead and I'm going to go make a blank list of means. I'm going to go for range underscore. So this means I'm not using this down in the for loop right here, just to signify that I'm not going to use this. for in range means. So I'm just going to repeat this 100 times. Okay, so how many n means do I want to collect? The number of essentially samples, I guess you could say I want. Okay. In the way I'm going to randomly sample this, I'm going to use numpy.random.random integer, because if it's an integer, I can use that to logically index, or not logically index, just index into my data frame or my numpy array. I'm going to go from blank to the number of values that I have in my array, size equals sample size, okay, which is 200. And then I'm going to append, I'm doing a couple things right here. I'm going to select the values from this index based on an array. And so this is the way that you can select index values from an array. It's just these square brackets right here. Normally in pandas, just if you remember, it'd be dot. Okay, to do this, it's not pandas in numpy, right? Data types, we got to pay attention to those. And so a numpy array, and then what we're going to do is we're going to select random rows. We're going to get the mean of those rows, and then we're going to append this to the means list up above. Okay, then I'm going to create a figure. I'm going to then do x.histplot and putting the data, the means, the alpha 8. And then what I'm going to do is 4 rectangular patches, the line width, the edge color, give it a nice kind of like white edges. Trying to be fancy. Show you guys everything you can do with Seaborn in this lesson as well, side lesson. Okay, then putting the plot in with the title of the plot, the uniform right here, no Y label, tight layout. And tight layout is just going to make sure everything sits nice. It's not necessarily going to make it tighter, but it's going to make sure everything's kind of sitting spaced out nice and stuff. It's always a good idea to do, especially when you're doing more advanced stuff like this, but it's more so when you're adding a few things in the plot would be the most appropriate time, but this still works here. Okay, and then plot. So now we can, every time we run this, it should be a little bit different. Sometimes a lot different, sometimes a little bit different. But notice it's almost always, let's see if we did 5,000. It's, and it gets closer to that normal distribution the more samples we take, right? And so this is coming from a uniform distribution. Just wanted to show that if we do the same thing from a normal distribution, also going to get a normal distribution, no surprise there. We only took 10 samples though, you know, even from a normal distribution, 100 samples, you know, it's starting to emerge, but it wouldn't really call that normal yet. But as we get to 1,000 samples, it really starts to take on that normal distribution. At 1,000,000 samples, and it's perfectly a normal distribution, which is just really interesting. This is the concept of how we can use hypothesis testing. So they're going to say at a certain level, we can be 5% sure that it's caused by random chance, that this is, you know, we got the average one time and it was right here, but sometimes we'll get an average and it'll be over here, sometimes it'll be over here, sometimes it'll be over here, sometimes over here. So if you get an average that's right over here, you can be sure that it's so far out of the middle of this distribution from the accepted mean, you can be that it's so far outside of the generally accepted mean from before and your null hypothesis. And if you get an average over here, what this is going to say is, well, I'm, you know, sure that this could only happen 1% of the time because of random chance. And so it's likely that I'm going to believe these results. That it's not very unlikely that it was just random chance, especially if I was diligent in how I collected my sample. But you can see again, this is how we would use it. But because of this shape of the central limit theorem, where we get the normal distribution from resampling, which is super weird, but it works really good. It's kind of cool that we can do this. And then just to show, I'm gonna get an exponential distribution, random. There's different types of exponential distributions. The one that we normally talk about is the standard exponential and exponential distribution. And then as you get the simple means from it though, just a normal distribution again. Normal distribution again, or merging already. If it was abnormal, what I'm going to do is numpy.concat. I'm going to concat the two distributions together. Then what we would do is plot in the normal distribution. You can see abnormal. If I sample from that, even, well, after 10, it's not so much, but 100, start to see something of a normal with an outlier. But 1,000, you can really start to see that normal distribution emerging. Okay, it's really kind of cool that we get that normal from an exponential and abnormal, really weird looking distribution. We can get the normal distribution at the end. Okay, and then again, so now let's try this on a data set. Let's play around with this and see if we can notice the subtle differences between, we have a sex column in this, we have a population column. So between two different categories here, and if we can really start to notice between sex and population, there's differences in any of these features. So more than just getting the average and saying, okay, well, the average is different. You can see here, skull width, 56, 57. I don't know if you can really statistically say that any of these, because it could just be random chance, right? You could have got a random sampling of females that just caused your average to be a little bit more to one side or the other side. And so you really can't statistically say that, I'm looking at this, that any of these really are actually different. But is that really true? So let's look at this in a little bit further case. So we looked at by sex, by population. There is, I'm just trying to remember if there's one, foot length was one of them that was quite different. But that's about it, which is really interesting. Okay. So I'm going to redo the plot histogram with a data frame this time. Just a slightly different value here. So what we're going to do is we're going to go plot the histogram with the df with the data frame this time. The x value is the value that we'll be giving it right here, and then patches is the same, title, no y label, and tight layouts. Okay, so if we run this, plot history right here. Okay, so define the skull width by sex. You can see they're pretty overlapped, right? Nothing really too surprising there. And then total foot length, you can start to see a little bit of a difference here. And then population foot length. And we saw that was one of the bigger ones by population. So it's the most distinct differences. There's still a lot of overlap though. So the thing is this likely would not pass hypothesis test, because you could easily say that more than 5% of the data is, they're overlapping, especially with this over here. So can we get a good sense of, we'll play with this today and you can see ear conch is quite different. That one's maybe a little bit easier, but we'll play with this and see if we can really tell the subtle differences and become a little bit more confident in this through hypothesis testing. Okay. So null hypothesis, it's always a good idea to write them out, truthfully. Okay, so null hypothesis is skull width is the same. And that's the generally accepted kind of boring principle that was there before. You're trying to change this concept like the phoenix rising from the ashes to make sure that, we're trying to say that something is different right here. So then is lower than the male. The way that you would do this in, I guess, classically is using stats model dot stats weight stats z test right here. Run the z-test on this mean. So I'm going to get the mean of the males, and then what I'm going to do is I'm going to say the female distribution right here, logically indexing, selecting the value column and saying value of mean, and I'm going to say that it's smaller, okay? So now it's interesting, we get a 0.05, okay? That's nice, 0.05, so it's not technically, we wouldn't technically pass that, but let's see if we can inspect this a little bit more, because I feel that, there's probably a good difference, right? It's just didn't pass, right? So 5.1% of a chance that it's random instead of a 5% chance. So, but as you plot this, really, you're kind of getting that sense that, it really doesn't seem like they are different, right? And so let's see this with hacker statistics, okay? So if we look at this, what I'm going to do, just to highlight what I'm going to do first, I need this to do the colors in the legend. So I'm just going to create 2D lines. I'm going to create two colors from this, color palette 1, 0, and 4, and putting it into this. Okay, so it's creating custom lines that I'll use then in my legend, just to kind of make everything line up. Feet and skull width right here means 1. I'm then going to do mean right here of the one distribution. I'm going to get 1,000 samples. I'm going to append all of those samples to means 1, and then I'm going to plot that data after I make a figure, plot the data, and we're going to go for rec, and then we're going to do the outlining of the bars for rec and AX patches. Then I'm going to do the mean from above and plot the vertical line. Okay, plt.title, y label none, legend right here, and this is where I'm adding those two colors for my custom lines, and then labeling the plot is because I did two plots on top of each other, so you can't just call the legend and it'll work, unfortunately. We had to put a little bit, because we're doing kind of a little bit of an interesting thing here. Tight layout and then show. Okay, so I just wanted to show, making that step by step. It's not so bad. Okay. So you get that distribution right here. To do a little bit further though, so this is just plotting it right here. Okay. Oh, gotta make sure you run everything. Okay, so we get our little distribution. You could say it's not, there's probably more than 5% of the data over here, so it's kind of, it's not really, it is different, but it could not be as well, right? So, okay, so getting into how we'll build the this plot, a little bit of bootstrapping analytics here. Okay, so, or hacker analytics, I guess you could say. So if we're gonna do this, we're gonna do the sample collecting of the means, but we're gonna do that 100 times. Okay, so what we're gonna do is we're gonna collect 80 samples of 50, and then get the index numbers, select the index numbers. This is using pandas though, so just to highlight that, I'm gonna reset the index just to make sure it's 0 to whatever number, because I'm logically indexing it, so it would be kind of a broken ordering of numbers in terms of that, because we're just going to get the ones that are female. I'm going to reset that though, so I can then randomly sample just the index values based on the length. So 0 to the number of rows, and that will be the index values that I'm going to select from that. Okay. So then I'm going to get the mean and append that to the means list right here. Okay. I'm going to plot that right here. I'm going to do the patches that we've seen before. I'm going to add I'm going to create a big list of the sample means right here. And then the very end, I'm going to plot the mean from the original, the alternative distribution. Okay. And then everything else, I guess the title, set label, custom lines, tie layout, and show are all the same. Okay, and so as we look at this, you can see there's quite a nice little tail right here. Quite a long little tail, but they're very really likely outliers that are causing the situation. So sometimes the males or the females are larger, but this could be like an outlier situation. So it doesn't really seem like there's a lot of data or a lot of means over here to really support that it is larger, right? So we saw that it barely failed the hypothesis test that females are smaller than males. And I guess you can kind of see it, but you get a better understanding now of the hypothesis test. Where did that number come from, right? So what's kind of cool is we can go all sample means to greater than mean, and so greater than this, and we can see all sample means. So there's only 5% right there. So again, it's very interesting now. We got a very close answer to what we got when we did the hypothesis testing. So we're able to brute force this and now visualize this. And okay, yeah, so it failed it, but I'm still actually going to be pretty confident though. There's going to be some random females that are quite large, but most of them in general are going to be smaller than the population of males, would be what I would expect if I would go there. Okay, so again, a very, very close score between the two. Now we're going to put that whole function that I did up here into, or sorry, the whole thing that I did up there into a function. So you could see that was very long. So I just did the exact same thing and put it into a function. And if we plot this right here, it takes a little while to do these ones. Okay, and so there you can go. We see the whole plot now done like this with our plot, all in a little nice clean one line of code. Well, a few lines of code, but a nice little function that we can just keep our notebook clean. Okay, so I wrote a little bit about what to interpret from hacker statistics. Go ahead and read this after. I'm not going to read this to you in the video, but you can go afterwards and read through this and get a little bit more detail. I know this is confusing the first time you see it, but as you keep using it, you'll start to get a better sense of really what hypothesis testing is, what sampling causes, and what you can believe in when you take a summary statistic, how much you should believe in that summary statistic. Okay, so looking at the females here, and what we're going to say is males and females are the same length. Okay, so just going to do a two-sided test now when we do the z-test from stats model that we imported up above, and we say 0.1, 0.01. So no, I would not say when you look at this that they're any different at all. Okay. So we look at the hypothesis test. Foot length is different than population. So let's look at this, and we can see that it looks quite different when you plot it. And you can see you got a very, very low p-value here. Okay, so just looking at the more traditional way to do hypothesis testing here as well. Okay. Looking at a two-sample test, so looking at the total length, population, class 1 and class 2. So highlighting what those are, Vic and other. I do it like this because I know I'm going to put this into a function afterwards. So if I have my arguments right up here when I'm writing this, it'll fit very nicely into a function when I put it down here. Okay. So if I could plot, I'm going to do two samples though, because I'm going to get two different distributions instead of just one this time. Okay. So we're looking to see if two distributions are different. Okay. So ear crunch is different by population. Okay. Smaller or larger, but just different. Okay. And so here we're going to do our index 1, index 2, sampling those sizes. Then we're going to reset index and sample from that index. And then plotting two different histograms right here. And then after I plot both of those, they'll be in the same plot. So then I'm going to iterate through the rectangles, change the line width of those, and then set title, Y label, legend, and then type layout and show. Okay, so doing all of those. So we get a sense that they look pretty different. It's interesting. There's still a lot of overlap, but you're getting to see that little smaller tail that kind of comes out right here. And really the blue kind of just truncates. It just kind of seems to end right here. Sometimes I don't really see any boxes that go any more than that. Okay. Throwing that all into a function. Okay. So we looked at ear conch by population in Vic, you can see. Okay, and you can see, well, that was pretty easy there. They're pretty different right there. And then we collect the averages. Okay. And then total length, what does that look like? So now here we're getting the total length here, and you can see, really, I mean, even the thing is, we could see that the populations were a little bit different, especially by foot length. But really here you can see that sometimes the means of ones is even lower than the other side, right? So, I mean, it's very easy to see that these are not statistically different right here. You got the mins are basically the same, just a little bit on the outside on one of them. The maxes are, again, sample 1 and sample 2. They're very close to the same. You can see here 91 and 89. So we got them very, very close. So basically these distributions to me would be overlapping. And if we look at this in a p-value, you can see you get a 17% p-value. I would actually put that up at higher, that they're from the same distribution, truthfully, after looking at this and understanding the actual hacker statistics, how these are going to plot out. If that's only 17%, that would surprise me. It gives me more confidence here that there is no difference, right? 17% chance that they're from, they are the same. I'd say it's a lot higher than that, truthfully. And so that's kind of the idea here, is we're just getting a better understanding. So, and you can see, again, a little bit more about how to understand p-values here. Okay, so thank you so much for joining me. I know that was a little bit of a confusing class, but go through this, play around with this, and we'll use this in the next class to help us highlight some subtle differences that we weren't really able to find in any other way. Okay, so thank you for joining me, and I'll see you for the Data Analysis Bootcamp number 10, and we're in the home stretch.